Welcome to example number 14 on the rotating rod. So we have a uniform rod with a length L and mass M that's attached to one end of a frictionless pivot point. And it's free to rotate, and it's going to rotate in this direction. And we're asked several questions. For example, we're asked, what is the initial acceleration of the rod at the very beginning, both angularly and linearly? B, if we were to place a penny right here at the very end of the rod, would that penny stay in contact with the rod? If it does lose contact with the rod, where would you place the penny on the rod so that it does stay in contact with the rod? Part C is asking about using conservation energy to determine the angular speed when the rod gets to the very bottom over here. What would be the angular velocity and what would be the linear velocity? Both of the center mass and the very tip of the rod down here. Okay, let's get started. So in part A, we're asked to determine the initial angular and linear accelerations of the rod. So let's take a look at this point, this rod, right at the very beginning. So we'll call this part A. So if we were to look at the rod itself and draw a free body diagram, we would see that there would be a force of gravity acting right here at the center of mass. And that is producing a torque acting on the rod that's causing it to go in the clockwise direction. So if we apply Newton's second law, the angular version, sum of tau equals I times alpha, we have a torque that is being produced by the weight of the rod. That's the force of gravity. So we have the force of gravity multiplied by this distance here. So that is the radius of this turn, so r, which will be equal to half of L. So the torque would be the force multiplied by the distance r multiplied by the sine of the angle between the arm and the force, which is 90 degrees in this case. So sine of 90 degrees is 1, and this is equal to I times alpha. So we can replace the force of gravity with mg, and we could replace r, the radial distance, with L over 2, and that's equal to I times alpha. Now, we do know that this is a rod that's being pivoted at the very end of this, so we can find out the rotational inertia of a rod being pivoted at the far end of it. If you go back to your notes, you can see in our table of common geometric shapes that we're looking at the long thin rod, but we're not rotating about the center, but rotating about the end. So we're using this situation, and so our rotational inertia is going to be 1/3 ml squared. So we're going to replace our rotational inertia, our moment of inertia, with 1/3 ml squared in this expression. So we have mgl over 2 equals 1/3 ml squared multiplied by the angular acceleration. You'll see the mass cancels out, making it independent in this problem, and one of the L's cancels out here. And solving for the angular acceleration, we're going to get an answer of 3 g all over 2L. If we were looking for the linear acceleration, all right, and I see that I've got this worded incorrectly. It says, what is the initial acceleration of the rod and the initial linear? So it really should be, so the initial angular acceleration of the rod and the initial linear acceleration of the rod. So if we're going to be looking at the far right end, by the way, at the beginning, all of the points on the rod have the same angular acceleration, right? But they will have different linear acceleration. The further you are away from it, the greater your linear acceleration. If you recall, the linear acceleration is given by r multiplied by alpha. And in this case, r would be the distance all the way to the other end, which is going to be L, and alpha is what we just derived as 3g all over 2L. And so you can see the L's will cancel out, and the linear acceleration will be equal to 3/2 of g. So what does this mean if you were to place, say, a penny at the very end of the rod? would it stay in contact with the rod as it fell? Well, if you see, we've just determined that the linear acceleration at the far right end of the rod is 3/2 of g. And the penny, let's say if it did lose contact with the rod, it would be only accelerating at the rate of g. So since the penny accelerates at 9.8 meters per second, yet the right end of the rod is accelerating at 1.5 times that, that means the penny is going to lose contact with the rod. So then what location would you put the penny so that it would not lose contact with the rod? What minimum location? Where would you have to shift this penny so that it would continue to stay in contact with the rod? Well, for the penny to stay in contact with the far, some point of the rod, we need to find the location where the acceleration of the rod is exactly equal to the acceleration of the penny, so that both of these things have the same accelerations. So we want the acceleration of the penny to be exactly equal to the acceleration of the rod. The acceleration of the penny we know is g, and the linear acceleration of the rod will be equal to 3/2 g if you are at the far right end of L. But we're just going to use r times alpha. But remember, alpha is the same initially. It's equal to 3g all over 2L. And now you can see there's a g on both sides, which you can cancel out. And if we rearrange for r by itself, you're going to find r to be equal to 2/3 of L. So essentially the penny needs to be 2/3 of the distance of the rod from the pivot point. So 2/3, so 1/3 away from the right end, so that it will stay in contact. And any of the pennies, if you were to place a penny here or here, all of these pennies would stay in contact. And if you follow the link that I have shown here, you'll see a video of another teacher showing this demonstration in class. I'll try to show it to you as well in class. Okay, let's move on to part C. We're going to be using the conservation of energy to determine the angular speed when the tip of this rod is at the very lowest point. So let's take a look at part C down on the lower part of the page. I'm going to redraw this diagram down below. And so here I have the picture of the rod initially, and this is at the very bottom finally. It's important to realize that in this example, the angular acceleration is not constant. You see, as the rod falls down more and more and more, initially the angle is at 90 degrees, but then as you go down here, the angle for the torque is not 90 degrees, and it's continuously changing, so that at the very bottom here, the force is directly in the line of r, and so there is no torque. So because the torque is changing, and sum of tau equals, say, I alpha, and since the net torque is changing, it's actually getting smaller, then the angular acceleration is continuously changing as well. It's decreasing. And so we can't use a method where you might, say, figure out the angular acceleration while it rotates from this position to this position, because the angular acceleration is not constant. So you can't take any approach of saying, oh, I found the angular velocity, and then use something like omega equals omega naught plus alpha t, or omega squared equals omega naught squared plus 2 alpha and delta theta. You can't use any of that. Why? Because the acceleration angularly is not constant. So the only way to really solve this problem is really use a conservation of energy approach. So the energy initially is equal to the energy finally. The mechanical energy of the rod and earth system is conserved. And since we're looking at the rod and earth system, we're going to assume all of the mass of the rod is concentrated right here, which is at the center of mass. So down over here, right in the middle approximately, there's the center of mass. So when solving this problem and looking at the energy initially, hopefully you realize you have some gravitational potential energy. I'll just write this as mgh. And then as it falls downwards, it's being converted into rotational kinetic energy, which is equal to 1/2 I times omega squared. So we're going to assume that the gravitational potential energy is going to be 0 at the center of mass right here at the lowest point. So right here, we're going to assume that is 0 gravitational potential energy. So the final height h is 0. So when you look at, say, mgh here, the final potential energy will be 0. So I won't even bother writing that term in. You really only have just rotational kinetic energy at the bottom. At the very top, it has potential energy, and that height that has gone up right here is equal to, well, this is the length L, or this is the length L in here, so that's going to be equal to half of L, because we're going to be assuming that the mass is uniformly distributed over the rod, and hence it's in the middle of the rod. So we're going to replace H with L over 2. And on the right side, I have 1/2 times I omega squared. Well, do we know what the I is for a rotating rod at the pivot point? Well, yes, we do. Remember we learned that earlier. That was equal to, we looked it up, it's equal to 1/3 ml squared. So we're going to replace that into here. 1/3 ml squared times omega squared. So then we have some cancellations. We see that it's independent of mass, that rotational velocity. And these 2's cancel out as well. So if we were to solve for omega, it's going to be equal to 3 times g. Oh, and I also see this L. One of these L's cancels out with one of these. 3g all over L and the square root of that. So that's the angular velocity of the entire rod. Now remember, the angular velocity of all of these points are all the same. What's going to be different will be the linear velocity of, say, the center of mass and the linear velocity at the far right end. So how do we find out how fast the rod is at the middle and, say, at the very tip? Well, that's where we use the velocity is equal to the angular velocity multiplied by r, the distance away from the pivot point. So if I'm looking for the velocity of the center of mass, I'm going to be using the angular velocity of 3g all over L. And then r is this distance, which is half of L. So L over 2. And then if we rearrange this a bit more, we get the velocity of the center of mass to be equal to 1/2 the root of 3gl. So that's the velocity of the center of mass. What about the velocity at the very tip of it? The velocity at the very tip of it, will be equal to the angular velocity, which is root 3g all over L, multiplied by the distance from here to the very end right here, which is going to be just L. And so then you're going to get an answer of the velocity of the tip is equal to the root of 3gl. Hopefully that makes sense. You can see that the velocity of this, maybe it's going like this, and the other one's going to be going twice as fast as that. So this is twice as fast as the middle. In fact, there would be no velocity right there at the very pivot point. And this would be consistent with what we were doing earlier about the acceleration. Remember we talked about the acceleration is going to be greater at the very end. It was like 3/2 of g. It was accelerating at a greater rate than the acceleration due to gravity. And about 2/3 of the way from the rod here, that was at the acceleration of g. So therefore, if you have a higher acceleration here, you're obviously going to have a faster velocity at the very tip of it as well. So it's important, as we look here, this is part D, as you look through here, when you solve for angular velocities at a different position, you cannot use, say, sum of tau equals I alpha, as I mentioned earlier, because A, or alpha, is not constant. And because it's not constant, you can't use sort of rotational kinematics equations because you do not have constant acceleration. So the only approach you really can do with C and D is actually a conservation of energy approach. And that's it for this example.